baby shawties, welcome to our next unit. In this unit, we're going to focus on the concept of sound and some of the properties of sound and some of the different phenomena that we have with sound, including things like music and all that. So a lot of the stuff we're going to learn about in this chapter is going to be very similar to what we learned about last chapter on waves. Sound is technically just a different type of mechanical wave. Last chapter, we primarily focused on what are called transverse waves, where the medium would vibrate perpendicular to the direction of motion. So again, if I have my rest position of whatever my medium is, say it's a string or a rope or something, that I would force a vibration up and down while the wave itself traveled forward through the medium. So sound is a type of wave. The only difference between what we're going to look at this chapter and what we looked at last chapter is that sound is a longitudinal wave. Now I have some different visuals here. Longitudinal wave, again, is where we are going to see the wave vibrate parallel to the direction of motion, okay? So you'll see here that in each of these diagrams, we're going to see the wave moving to the right. But as you watch the vibration, you'll notice here, like, for example, the tuning forks, you'll see the prongs of this tuning fork vibrate forward and backwards, and if you watch the dark spots travel through, okay, the wave itself is still moving forward through the medium. Same thing here. We got the string. Think of this as like a guitar string that's plucked that's going to make a sound. It's going to create that vibration that travels forward. But the idea is you get the medium itself moving forward and backwards as the wave moves forward. So it's a little bit different than a transverse wave in just simply the direction in which the objects are vibrating. Now, a couple key components of these types of waves. You have the points within the medium where, since we're moving forward and backwards, you'll see, especially here, you'll see the places where you have, you'll see the places where you have the dark spots and the light spots. So understand there was two different things that we could see. The dark spots are where the medium is compressed. So those are called compressions. Technically, a sound wave is also called a compression wave because what happens is all the molecules in the medium, say for example air, are all densely packed together, forming a compression. And then next to every compression, think of it as a rarefaction. Okay, rarefactions, again, are where the things are spread out. It's rare to find particles in those positions. So as you see this video, pause here, this area right here, this would be considered a compression, and the area between would be a rarefaction. So you have the alteration between compressions and rarefactions. This is very similar to transverse waves. You have crests and troughs. So the way we're going to kind of compare these is, think compressions we're going to treat like crests, and think as rarefactions we're going to treat like troughs. So even though sound waves are somewhat different, we can view it for our sake almost as a transverse wave to help things make sense to us. So here's kind of a visual of what I'm talking about. So up here in this top picture, this is what a sound wave would look like as it travels through a medium. So all these little dots are particles within the medium. Could be air, could be water, could be a solid, for example. But you'll see these positions where we have our compressions. That's where the particles are densely packed together. And you have the rarefactions where they're very spread out. So again, treat the compressions almost like crests and the rarefactions like troughs. It's a good way for us to visualize things in a transverse way because it's helpful for us to visualize what's going on. And it helps us then to make comparisons between what we talked about last unit to what we're going to talk about now. Because we looked at the very basic properties of waves, and there are some specific phenomena that we're going to look at with sound waves. Okay, so what we're going to go through are just the basic properties of sound waves and some of the basic properties of waves. So the three things we're going to look at today are wavelength, amplitude, and frequency. So things that we talked about as a very introduction to waves in general. We're now just going to look at it. What do these things look like in terms of sound? So wavelength doesn't really change much, and that's why we're going to start off with this one. Obviously, the wavelength, we looked at the length of a complete wave. And a complete wave we talked about from last unit in terms of like a transverse wave was a complete crest and a trough. So the wavelength would be the distance from that point right here on the wave to that consecutive point. The formal definition of wavelength is technically the distance between two identical positions on a wave. Okay, and those positions have to be like consecutive. So meaning like it could be from a trough to a trough. Okay, it could be from a crest to a crest. All those distances are going to be the same. They could all be represented in terms of the wavelength. So if you kind of compare that to what I'm showing up here, all right, if the wavelength can be viewed as a crest to a crest or a trough to a trough, then on a sound wave, the wavelength is simply the distance between two compressions or the distance between two rarefactions. So that would be considered the wavelength of my wave. It's a little bit different in terms of the longitudinal wave, but it's still kind of the same thing. We're still going to measure these things in meters. It's still a distance or a length. But again, as we visualize these compressions and rarefactions, a little bit different. But again, it's the same thing when you kind of view it as a transverse wave. All right, the next basic property we looked at was frequency. Now, in terms of sound, especially those of you that might be or might know music, you might kind of know this stuff already, but frequency is the formal definition in terms of waves, is the number of waves you would have in a given amount of time. So the number of waves per second. Remember, we measure frequency in a unit called hertz. Okay, and hertz is just simply the number of waves per second. And it relates back to wavelength. Again, we can count the number of waves in a given amount of time. But again, we have high frequency waves where we have a lot of those crests and troughs. And again, think of crests as compressions, troughs as rarefactions. So you have a lot of compressions and rarefactions in a given amount of time versus fewer compression and rarefactions in a given amount of time. Now, in terms of sound, you can see here that frequency is going to be related to the pitch of the sound. The way I like to think about pitch is I like to think of how low the sound is versus how high, it's a sweet, the sound is. Okay, that's the way pitch is. It's how low versus how high. I tell you, my musical prowess is known throughout the world, folks. Now, this is where sound gets a little bit more interesting because sound obviously is an application of waves, but the human ear can only hear. That's very tough for me to say, but the human ear is only capable of detecting certain sound waves with a range of frequencies. It's actually a pretty wide range of frequencies. The threshold for hearing, I suppose, if you want to call it that, the low end, where we see our low frequency waves, the human ear can pick up around 20 hertz, okay? All the way up to a high frequency of 20,000 hertz. And this range of 20 to 20,000 hertz, this is normally what the average human can hear. Now, it does range because, for example, me being 32 years old at this point when I'm making this video, compared to, let's say, maybe you 17 or 18 years old that's watching this, there's a gap in years. I've listened to a lot of Lamb of God or Slayer and things like that, so my ears don't hear as well as they used to. So my range might not be as good, okay, as what you might hear. So there are some variants within this, but, above 20,000, that's known as what's called an ultrasound. So you might have heard that before. So anything above 20,000 is ultrasound. That means it is actually a sound wave that humans cannot pick up. They can't detect those. Those types of frequencies might be heard maybe by dogs or cats, obviously, or bats. Okay, you hear probably ultrasounds being used as kind of like a medical procedure that we can use. So that's kind of on the high end. On the low end is what's called infrasound. So anything below 20 hertz is what's called infrasound or infrasonic or something like that, okay? But those are any sounds that are going to be very hard, so low, I guess, in terms of frequency, it's going to be hard to hear. But in general, we can hear between 20 and 20,000 hertz. Now, I do have a video for you guys that's going to be kind of annoying. I'm going to jump through it a little bit because it is kind of longer. But what all it is going to be different frequencies. So I'm going to scroll through it and show you guys kind of the different sounds at different frequencies. And I want you to think about not only how it sounds in terms of like the low and the high, but as you go through this, I also want you to make note of if you can hear the certain frequencies. So for example, I'm going to start it off right away at 20 hertz. I cannot hear it. Okay, so I want to know when you can hear it. So I'm going to go maybe from 20 up to 100 and kind of jump around a little bit, all the way up to 20,000. I want you guys to think about what is the range at which you can hear these sounds. All right, so enjoy. Time out, I guess, before we get started. This is going to be really annoying, okay? So for those of you that get annoyed by different types of sounds, this can be tough. So maybe turn down the volume of those headphones, and I apologize, but I don't apologize. All right. So there's around 20 hertz. I can't hear a thing. Some of you probably can't hear a thing. So I'm going to increase the frequency. So it's be around 90 to 100. I want to go here because I start to hear it at about 120 hertz. Okay, so I'm starting to pick up a sound right now. Very faint. Very low sound. It's going to go a little slower, so I'm going to just move forward a little bit. He's around 500 hertz. Maybe a little bit more. So we're about 1500 hertz. Freaking annoying. I got a sleeping dog in the other room. Guarantee the thing's going to wake up. Ooh. Okay, I'm going to go up a little bit more. Okay, we're at, oh, nice. This beautiful sound. I love this. About 8,000 hertz. Fantastic. Okay, it's a sweet. Okay, now I'm just going to go down to, say, around 10,000 hertz. For me, when we get to about 10,000 hertz is when I kind of lose. This sound just is awful. Just awful. Right? Give me a headache. Okay, so it's about right now. I don't hear a thing. You guys might still hear something. I don't hear a goddamn thing. All right, and it keeps going. You can challenge yourself. You're probably really annoyed asking me to stop. But anyways, for me, my range is about 120 hertz to about, I don't know, it was 11,000 hertz. So my range is a little bit different than everybody else's. Again, that's what I can hear, okay? What I wanted you guys to get from that video is just obviously what pitch means in terms of frequency. So when we apply the idea of frequency to sound waves, you guys kind of have a sense of what it means. So think of it as high versus low. All right, what we're going to talk about next is the speed of sound. So we have obviously frequency and wavelength. Combined, those two things are going to make up the speed at which a wave travels through any medium. And this is the same for sound, okay? That depending on the medium itself, sound is going to travel through that medium with a certain speed. And then if you remember, we have that inverse relationship between frequency and wavelength. And hopefully you guys saw that as you went through that annoying video I showed you, that when we have very low, oh my God, when we have very low frequencies, we have very high wavelengths, but when we have very high frequencies, you got very short wavelengths. So it's an inverse relationship, and that is because the speed of the wave is always going to be constant, always going to be equal. So it goes back to what we talked about last chapter, that the speed of a wave, of any wave, whether it's sound or whatever, is always dependent upon the medium. And that is the case in this as well. So in terms of the types of mediums, obviously we have, like for what we hear air going through a gas. Think of that as going through air. But we can have sound traveling through, let's say, liquids. That's sloppy. Or solids. Sorry, my iPad's moving on me. Sound's going to travel differently in these. Think of sound, again, as a longitudinal wave where the wave is going to vibrate back and forth as it moves forward. So the wave is traveling this direction. The molecules are going to go vibrate forward and backwards within that medium, okay? Now, the reason why sound is going to travel differently through air, liquid, and solids is the density of it. Notice that gas is more spread out. So when this thing vibrates, the likelihood of it colliding with particles nearby is not as great. For a liquid, since particles are more dense, the likelihood of it colliding with other particles is greater. And for a solid, obviously this is the most dense we can see, so those particles are going to, no matter what, hit the particle next to it. So that being said, sound will actually travel fastest through a solid, then a liquid, and then the slowest in a gas. Okay? It always reminds me of the movie Stand By Me when they're, I don't know if you guys have ever seen it now, it's older. You guys don't know anything probably past 2000 because you were born in 2006. And nevertheless, Stand By Me was a movie back in the day of a bunch of kids that were walking down railroad tracks trying to find a body, whatever. And there's a point where they obviously walking on train tracks, they're on a bridge, and the train's coming, they got to get away from that. Now, what they could have avoided, how they could have avoided that situation was if they would have known the train was coming, okay? But obviously they're walking in or on the train tracks, and they're depending on that sound traveling through air, and it's not going to travel as fast. So if they really wanted to know if a train was coming before they went onto that bridge, they probably should have put their ear down to the train track itself, which is made out of a metal, very dense. Okay? They probably would have heard that train coming from a little bit further away, which maybe they could have avoided going on the bridge altogether. But then why would we do that in a movie? Because then it wouldn't be exciting, right? If a physics nerd made a movie and it was all physics like to a T, it wouldn't be as fun and entertaining, right? Let's be honest. Okay. Now, nevertheless, when we do look at the speed of sound in different mediums, obviously the one that we're familiar with most is air, right? We live in an atmosphere that has air. So the speed of sound through air can be found by using this equation, okay? And when we look at, again, what affects the medium, when we talked to last unit that the speed of any sort of wave is related to the tension of that medium and the linear density of that medium. Okay? Now, in terms of like air with a gas, what affects whether a gas is more dense or less dense? That is temperature. So you'll notice in the equation T stands for temperature. So this is just a simple equation that's going to give you the speed of sound at different temperatures. So for example, and this is all in Celsius, if I had 0 degrees Celsius, we would get 331 meters per second. So that would be the speed of sound at like a freezing temperature in terms of Celsius. If we take, for example, maybe, I don't know, 10 degrees Celsius, all I would do is plug in that number 10 where T goes. So I multiply 10 by this 0.6, and what it would do is just simply add 6 to this number. 0.6 times 10 is 6, so I would get 337 meters per second. Not a drastic difference in the speed, but it is going to affect. So in air, speed is affected by the temperature of that air. But in general, it's all, again, about the frequency and wavelength of that wave. All right, well, that leaves the last variable that we talked about with waves last chapter, and that is the amplitude. Now, amplitude in terms of a sound waves now has a little bit more meaning to it. Amplitude, again, is just how much energy that we're putting into a wave. Again, a wave is a physical disturbance. If it's let's say a wave in a spring, it depends on how much I'm shaking that spring or string, whatever it is. If it's a sound, it's how much energy I'm putting into that sound. The best way to do it is to think about your voice. I can talk really quiet at a whisper, or I can talk much louder. Obviously, the more I talk, the more energy that I'm putting into it. Think about me talking in front of a class first hour where it's nice and quiet versus me talking in front of my freshman math class at the end of the day when they're all sorts of squirrely, right? I have to use more energy to project my voice above them. Okay. Now, anytime we talk about the energy you're putting into something, that's called the amplitude. Now, in terms of the sound, we're going to think of sound or that amplitude as the intensity of that, which is also going to describe the loudness of the sound. So how loud a sound is going to be represented as the amplitude. Now, the way we're going to represent the amplitude or loudness of a sound is through a unit called a decibel. And you guys have probably heard this unit being used before. A decibel, again, is going to talk about how loud a sound is. So think about the decibels of a whisper compared to the decibels of a jet engine of an airplane that's flying over. Okay, it's going to be much greater in terms of the loudness of the sound. Now, the important part and why I want to go through this idea of amplitude is because we're representing the energy that's involved in that sound. This is what makes all waves special, is that waves are a way for us to transfer energy from one point to the next. So in terms of the intensity, sound is actually moving through a physical medium. So as it moves further away from the source of the disturbance, that intensity of sound is going to decrease. And this is where the decibel scale comes in handy. So when we actually go into measuring the intensity, we find the intensity by how much energy we put into it. But because sound travels outward in all directions, if I were to yell right now, it's not just going in one direction, it travels outward in all directions, okay? So think of it as how much power, energy you're putting into it divided by the area. And now why area is so important is that, let's say there is a sound, that sound's going to travel outward in all directions. So it kind of makes like concentric circles and travels outward in all directions. Now, as it travels outward in those directions, the further away you get from the source, the weaker that sound is going to be. It actually follows what's called an inverse square relationship. And the reason why it's an inverse square relationship is that the distance it travels is going to be related to the area, but we should hopefully know that area is measured in units of meters squared. So if I'm dealing with circles, the area of a circle is pi r squared, where r is that straight distance from the source, the center, to wherever you might be standing. So think of the r squared, that's that inverse square relationship. So here's the idea. If I'm, let's say, standing 1 meter away from the source of that sound, let's say my intensity is 160 units. When I go 1 more meter away, notice it didn't just get cut in half. Okay, what happened is that it was cut in fourths, 160 down to 40. Now again, if I were to continue this trend, here's how we can look at it. Let's say I want to look at, okay, I'm doubling the distance. So I went from 1 to 2. Let's say I skip 3 and go 2 to 4. I double the distance. Notice the intensity goes from 40 down to 10. So it's dividing by fourths. So this is that inverse square relationship that we have. And the idea here is this is how the decibel scale is developed. The decibel scale is all developed on what's called the threshold of hearing. Okay, it's kind of a scale very similar to the frequency we talked about before. That this is more so of what the human ear can handle and what it can hear. So in terms of intensity, kind of like frequency, we had the kind of the low end was that 20 hertz. In terms of intensity, the low end, the threshold of hearing, this would be like the quietest sound that we could hear, would have intensity of 1 times 10 to the negative 12 watts per meter squared. Now I want you to think of that, okay, that unit's weird, but 10 to the negative 12th is a very small number. And when I'm talking small number, I'm talking about 11, that's 6, 7, 8, 9, 10, 11, and then a 1. That's 11 zeros and then a 1. That's almost like zero intensity, okay? And then when I get all the way up to, let's say, a jet takeoff, we have a power of 10 to the second. 10 to the second is saying 100. So in terms of when we use like the power and area, the units we're getting or the values we're getting are very small. They're very small and they're not representative of what we see in real life. So the decibel scale is just a scale that we use that kind of fits the numbers to what the human ear can actually handle. So the lowest sound that we can handle, that we could even hear, the threshold of hearing, we just now say, okay, that's going to be 0 decibels. All right, and then as we jump up, notice it's going to go from 10 to the negative 12th to 10 to the 11th, 10 to the 10th, 10 to the 6th, and so on. So if I just track these, as I go from 10 to the 12th to 10 to the 11th to 10 to the 10th, I want you to notice how the decibels go up 10 every single time. Sorry, not the 60. And that's how the decibel scale works. It looks at powers of 10. So if I were to get a sound that's 10 times greater, that's going to mean it's 10 more decibels. If I get a sound that's 1,000 times greater, it's 30 more decibels. We're going to think of it as the number of decibels as just simply looking at the power of 10 that we would have. Okay, that gets a little confusing, so let's go through some examples. So let's say, this is the stuff that I'm going to be asking you guys to do here for your practice. Let's say that I have a sound source A, and that the sound source has a decibel rating of 70 decibels, okay? And let's say sound source B is 10 times more intense. I want to know what's the decibel rating for sound B, okay? So this decibel scale is all based upon the human ear and what we can handle. That threshold of hearing, the very faintest sound that we can hear, is 0 decibels. As we jump up in powers of 10, every power of 10 is another 10 decibels, okay? So in this case, it says that we are 10 times more intense. How the decibel scale works is all based upon power of 10. So when I think of the number 10, technically as a power, it's 10 to the first power. So when I look at sound source A, which is 70 decibels, what I'm going to do is I'm going to add 10 decibels for every power of 10 that I'm greater or potentially less than. So when I look at this number, I'm going to notice that it's 10 to the first. So I am 1 power of 10 greater than my source sound for A. So what I'm going to do is I'm going to take 70 and I'm going to add 10 decibels to it. And that's going to give me then 80 decibels. So that means my sound source for B would be right next to it at 80 decibels. So for every power of 10, it's 10 decibels increased or potentially 10 decibels decreased. It's a little bit confusing, so let's go through a couple more. So here it says sound source A has a decibel rating of 60 decibels. Sound source B is now 1/100th the intensity. So we have 100. Think of that as 10 to the power of 2, 10 to the second power. Okay? The key thing there is that power of 2. The power of 2 means that we are going to work with, in terms of decibels, we're going to work with 20 decibels, whereas this was working with 10 decibels. Now here's the only difference between this problem and the problem that we just did. Is the last problem it got 10 times more intense. Here it's 1/100th. That means it's going to be less intense. So what I'm going to do is I'm going to start with my 60 decibels and I'm going to subtract 20 decibels to give me 40 decibels, which means sound source B would be right here below it at 40 decibels. Okay, so we're dealing with the powers of 10, and we're going to be adding or subtracting 10 decibels based on that. All right, let's see if we can figure out this last one. So in this last one, we have sound source A is at 50 decibels. Sorry, it says 60. That's supposed to say 50. Whoopsie daisies. Okay. Sound source B is 1,000,000 times the intensity. Holy strawberries, Batman. So what we're going to deal with again is that number 1,000,000. 1,000,000 is technically 10 to the 6th power. So we are going to look at that power of 6, which means we're going to be dealing with 60 decibels. Now in this case, since it's it's 1,000,000 times greater, we're going to start with that 50 decibels, and we are going to add 60 decibels to that number, which is going to place us at 110 decibels for that sound. And that 110 decibels, let me tell you, it is going to be a very intense sound. I don't know what that was joking. It's kind of like camping. You know what I'm saying? Intense. There was the joke. I get it. But anyways, for B would be right there located at 110 decibels. All right, so in this video lesson, we looked at kind of the basic properties of sound waves related to just the basic properties of waves. So wavelength, frequency, wave speed, and then lastly, the amplitude or intensity. So know that all these things, nothing really new, but kind of new in how we view sound. Get it? View sound, because we don't view it, we hear it. Nevertheless, folks, as always, you got any questions, jot those things down. Good luck on your practice problems. We'll see you next time. Peace out.